Hello, everyone. It's great to be back after a couple of weeks break. It's my great pleasure to welcome today's speaker, Dr. Theresa Saxton-Fox. She's an assistant professor of aerospace engineering at the University of Illinois at Urbana-Champaign. She received her master's and PhD from Caltech and did her postdoctoral research at Princeton prior to starting at the University of Illinois in January 2019. Her work focuses on wall-bounded turbulent flows with particular interest in nonlinear interactions, global unsteadiness, and curvature effects. She was awarded the Centennial Prize for Best Thesis in the Mechanical and Civil Engineering Department at Caltech in 2018, and also the Young Investigator Program Award from the Office of Naval Research in 2021. And I'll hand it over to Tess.
Thank you so much. So I'm Tess or Theresa. If you can't hear me or anything's wrong, please let me know. But otherwise, I'm really excited to be here. I'm really excited to chat with all of you about this work. There's obviously phenomenal turbulence research being done in Australia, and really excited to get to chat with those of you on the call. So I'm going to focus today on some of my work on the organization of structures and wall-bounded flows, and some of this comes from my PhD work, and some of this comes from work that I've done at the University of Illinois. So I'll jump into that, but I'll just give myself one slide to highlight some of the other cool things that we're doing. So I want to first acknowledge some of the students. So Elizabeth has done a lot of the work that you'll see in the second half of the talk. Sharia also contributed some, and Akil has done some as well, and then also Adi Partha Sarathi will highlight a little bit of her work too. But as I'm sure all of you know, graduate students do a bulk of the research that we present. I also want to highlight some of my collaborators, my PhD advisor, Beverly McKeon, and then Adrian Lozano-Duran, who's at MIT now as an assistant professor. In my funding, I have some of this work is being funded by NSF from a graduate research fellowship, the National Science Foundation of the United States, and also a grant. And then I might at the end get to a little bit of work that's being funded by my Office of Naval Research grant. And then some of my PhD work was funded as well by a United States National Defense Science and Engineering Graduate Fellowship. Okay, so my acknowledgements are out of the way. What are we going to talk about today? So I'm going to focus today talking a little bit about large and small scale structures in a turbulent boundary layer. This is something that many people at Melbourne study and just is generally studied by a number of people in turbulence. I'm going to look at it both as it naturally occurs in a turbulent boundary layer and also at the interaction of a turbulent boundary layer with a cylinder wake. So I'll put a very small cylinder in my boundary layer, which will shed very small vortices, and I'm going to see how those vortices in the larger structures of the turbulent boundary layer are interacting. And my aim here is really to try to distill out and ask questions about the fundamental mechanisms that are underlying these interactions, and how do we distinguish different potential mechanisms through careful data analysis. I also just want to plug a totally different topic that my group is doing, but I'm letting myself advertise it shamelessly here. We're doing some really fun work on temporally and spatially varying pressure gradients experimentally. So we have the capability of rapidly changing a ceiling configuration. In this case, it's a simple U shape, really, that we can change very quickly, and that gives us a tremendous amount of power over the pressure gradient in space and time. We can change this at will, and we can choose any fixed position in between the minimum and maximum, and change the rate of deformation if we want to. Anyways, these are just some preliminary results showing the mean velocity profiles at different pressure gradients that we can achieve, as well as the U squared. I just want to highlight that we have some fun data here. We have a paper that came out, and we'll be talking about this at the Turbulence Shear Flow Phenomena TSFP conference in July, if any of you are attending. All right, so let's talk about today's topic. So I'm really drawn to turbulence, and I have been ever since I was an undergraduate, when I learned in one of my fluid mechanics classes how prevalent and ubiquitous turbulence was. Turbulence coats planes, it coats ships, it's the very atmosphere that we live in. And I became really interested in turbulent boundary layers. And it was the interesting mixture of it seeming to be everywhere and to be relevant to many different problems I was interested in, from engines and drag to even the weather, but also that I was being taught these empirical correlations that didn't seem to have any basis in fundamental physics. And it felt like a clear sign that there was a lot of science here that wasn't well understood and that wasn't being translated into engineering, at least at the undergraduate level. And then I went to graduate school and I started studying well-bounded turbulence. And the thing that really got me hooked was the fact that there are structures, that there's underlying consistent structure of turbulence that we can identify and understand. This is a heat map essentially of where we see energy in a well-bounded turbulent flow from a paper by Monti et al. In 2013 that some of you may know. And on the left, they're showing it normal, kind of with a wall normal coordinate and a logarithmic, and here in a linear scaling for a boundary layer. And we can use this to tell us where statistically there's energy in a flow at what wavelength. So this says that at a wavelength of lambda x plus of about 1,000 and at a height in the wall of about 0.01, a little less, in well normalized by the outer length scale, we see this massive amount of energy at that wavelength. But if we go farther from the wall, we don't see energy there anymore. And instead we see it up at this larger wavelength. And we can look even farther from the wall in the linear regime where everything near the wall you can't see anymore. And we see that there's this other length scale that has this kind of clear peak right here. So it gives us, in the statistical way, a way of understanding that there are certain wavelengths at certain locations in the wall, from the wall, that have the most energy. And then we can understand that kind of physically as well. We can understand that these look like near wall streaks, that these are very large scale motions that we can visually observe by looking from the top. And these are what people call large scale motions. This can also be called superstructures for boundary layers. And we can visualize these instantaneously, and we can try to understand how the instantaneous structures are related to the statistical features that we can quantify. And this idea that there were these underlying patterns in a chaotic system was really appealing and has continued to be something that I'm really fascinated by and that motivates a lot of my work. So I'm going to ground us now in how I'm going to personally define the problem, and then we'll step into some of the technical details. So we're going to have a velocity field. I'm looking at a turbulent boundary layer. I'm going to define the mean as this overline U. I'm going to use the notation where Y is wall normal, which is distinct from what people often do in Australia, and Z will be my spanwise coordinate. X will be in the direction of the mean flow. I'll have corresponding U, V, and W, where uppercase indicates that I haven't subtracted a mean, and then I'll define lowercase as being my velocity field subtracted with the mean, temporal mean velocity. I'm going to largely be using spatial data, PIV data, and some computational data. This is a visualization of some data. We can see this is now, again, Y is the wall normal coordinate. We can see this kind of a bulge in the kind of outer region of the boundary layer, which is very classic. This is the kind of thing I'm showing. And actually, this is labeled wrong. So anyways, pay attention to this one. The uppercase means that I haven't subtracted a mean from this picture. That's my setup of the velocity field. I'm going to have a couple different sources of data. So some of my data is coming from my PhD work at Caltech. This is experimental particle image velocimetry, planar PIV data at a Reynolds number RE tau of about 900 and RE theta of about 3,300. It wasn't fully time resolved, but I could see the same structure like 5 times as it passed by my field of view, kind of a thing. And my resolution is shown here. I will say that this Y plus of 14.5, that's true, but nearest to the wall, the first couple of data points were corrupted by reflections. And so we don't really trust any of the data below about Y plus of 40. And then my field of view here was about a boundary layer and a half long. And then I also had access to direct numerical simulation data from Zhaowa Wu at the Royal Military College of Canada. And you can see details of that database here. I think it's a phenomenal resource. It's a boundary layer that starts laminar and they go through a bypass transition, and they simulate it all the way up until matching Reynolds number here. So I was able to get to an RE tau of 900 to compare to my experimental data. At the second half of the talk, I'm also going to talk about some work from University of Illinois. So this is a kind of long boundary layer facility that we've built to get us to slightly thicker boundary layers. So nothing like what you all have at Melbourne, but it's a nice facility for us. And we're going to put a cylinder in there and again look at wall normal streamwise planar PIV data at similar Reynolds numbers. So I'll get into this later. All right, so what are we talking about? So I'm interested in turbulent structures, and specifically this talk is about the organization of turbulent structures. And people have been interested in this for a really long time and have been finding consistent and interesting things about this for decades. So we can look back to Falco in the 70s to see observations of these kind of large bulges with vortices on their backs. And there was kind of this hypothesis that the mechanism there was that the vortices rolled up at the shear layer on these large scale bulges. Adrian in 2000, saw or hypothesized kind of this hairpin packet idea where these yellow kind of worms are vortices, and the mechanism there that was suggested was that they induce large scale slow motion below or within the hairpin legs. And so these are ideas coming from instantaneous data that are being kind of taken and understood from visualization and observation. There's also been, as I'm sure many of you know, a lot of quantification of organization using amplitude modulation. So there's lots of work here, especially from University of Melbourne. I'm going to highlight just two schematics that kind of show different ideas. So one, this is a schematic from Ganapathy Subramani in 2012, where they had large-scale slow structures, large-scale fast structures, and large-scale slow structures. And there was, again, this idea that there were kind of vortices in the backs of the large-scale slow structures, other rotation on this kind of edge, and then again here, but that near the wall, we also saw amplitude modulation. They saw amplitude modulation where the faster structures were associated with a stronger small-scale behavior. And this is a more recent work from 2017, again from University of Melbourne, showing that, again, in the presence of fast structures near the wall, the small scales are more intense. They're weaker near the wall with large scale slow, and it's the opposite far from the wall. And here, I think we can argue that this kind of suggests that there's true amplitude modulation of the wall, and there's more of like an organization everywhere else. Whereas this paper thinks more, I think, about kind of amplification from understanding the stress. So there's going to be more stress here. You can make arguments about that. There's more stress at the shear layer. Wherever we see more stress, you also see small scale amplification. And then I'm going to do some conditional averaging. So I'm also grounded in some work. There's obviously a lot more amplitude modulation work that I could highlight, but I'm going to let myself continue from there. There's a conditional averaging work also from Chung and McKeon. Berkeley McKeon was my PhD advisor, so I'm well versed in this paper as well. What they did is they took large eddy simulation data and they asked, using conditional averaging, if the large scale streamwise velocity field is slow at this x, what does the small scale do? Well, first they asked what does the large scale look like, and this big gray blob was that the region that on average was also slow if it was slow here. So it gives you a sense for the size of the large scale in this part of the flow. And then they asked what the small scales did, and they found that they strengthened above the x and weakened below it in this kind of an angled way when the large scale was negative, and it was exactly the opposite when the large scale was positive. When it was positive at the x, it was strengthened below it and weakened above it. I then this also kind of had a stress amplification idea. I did some instantaneous visualization of DNS at some point in my PhD. This is an example from that. So in the background, we have fast-moving large-scale streamwise velocity, slow-moving large-scale streamwise velocity, and fast-moving again. In the foreground, in white and black, I'm showing this kind of small-scale fluctuation. I've chosen a single isocontour to highlight, isosurface to highlight. And then in green, I'm showing the sum of this background with the mean to kind of show us how positive and negative corresponds actually to kind of like a wave in the total velocity. And we can again see the kind of organization we'd expect. So all of the things so far have suggested small scale activity and vortices are active above large scale negative and below large scale positive. That's been consistent in each of the literature pieces I've shown you so far that have been quantified in different ways. And we see it instantaneously in this picture too. If I scan across at a Y and delta of about 0.5, we see more small scale activity when we're in the presence of this large scale slow moving feature than we do in the presence of a large scale fast moving feature. So we're instantaneously observing, of course you can't make grand statements from a single instantaneous picture of turbulence, but in this one picture, it feels consistent with what's been observed quantitatively in the past, that small scales are more active above large scale negative and below large scale positive structures in a very general way. This picture, though, made us wonder whether there was the possibility of an advective mechanism, if somehow small scales could be thought of as being carried around by the large scales, rather than thinking of it as a stress amplification mechanism where small scales were strengthened in regions of stress. And I wanted to find a way of quantifying that question, of asking that question quantitatively. Can we distinguish small scales being strengthened by large scales in specific regions versus them being moved? So that led to the kind of analysis I'm going to show next. So that was a lot of rapid information, but the kind of key takeaway is there's this organization that's been repeatedly observed by a lot of different people, that small scale features and large scale features have a spatial organization, and there's a lot of different ideas about how that organization could be generated. To try to articulate my question, this question I wanted to ask quantitatively a little bit more cleanly. This is a schematic that's in this paper from 2022. So this schematic shows in red and blue these kind of prototypical large-scale inclined structures of the streamwise velocity field that are faster and then slower than the mean. And then in these little gray circles, I'm showing an idea of kind of small-scale activity. And I have two different visions here. The top one shows small scales kind of sitting at a particular height from the wall and either being weaker or stronger. So stronger is going to be darker and weaker is going to be lighter. And we see that they get, in this vision, they get stronger in this region of, higher stress, stronger here in the shear layer, and stronger here, again, in this region of higher stress. The lower picture has kind of incoherent, low energy fluctuations everywhere, but they have specifically coherent small scales that are spatially distributed along a particular area. And again, what I find interesting is that quantitatively, with many of the analysis techniques that we have, these two look very similar. In each case, if you were to average this, you would see strong small scale activity above the large scale negative, strong small scale activity at the shear layer, and strong small scale activity near the wall. So why do we even need to distinguish them? To me, the reason is because they suggest different mechanisms that might yield these behaviors that might fundamentally change how we understand how this is being generated and maybe also how we model it. So I was interested in whether we could distinguish these two behaviors. And so to try to do that, we came up with this approach, what we're calling conditional projection averaging, which is really a conditional averaging approach that uses a projection as our condition. So let's say this is our instantaneous fluctuating streamwise velocity field, and this is, let's say, our field of view. Let's say we have a smaller field of view than this whole visualization. Then what conditional projection averaging does is it compares that one snapshot to a model. This is a cartoon, of course, a model of what we think large-scale structures look like. And the idea here is that by comparing this, by which I mean projecting it, so I'll do a dot product, really normalized dot product, between this and each of the large scales at different phases. This is the same large scale kind of being artificially convected past my field of view. The idea is I ask basically, where is my large scale in its convection? Which of these phases is most similar to what my instantaneous data looks like? And if I did this projection for the snapshot, I would find that it looks most similar to this. You can see the kind of the blue matches the blue, the red matches the red. And so I would tag this instantaneous snapshot with an approximated phase of gamma equals 0. And I would then average all the snapshots that have that same phase. And so the idea is that this is, very similar to doing any kind of conditional averaging, but I'm trying to use more global information and leverage the fact that we actually do have good structural models now for what large scales look like that we can leverage. Of course, this is sensitive to the model you choose, and we can talk about that a little bit. We can write down mathematically what this is. I don't want to spend too long with equations, but we're really doing a projection of dot product normalized between the instantaneous streamlined velocity field at a given plane and at a given time, and we're doing dot product between that and some model, again at a given plane and at a given phase. And we're going to call that a projection coefficient. It's a function of which time instant you're considering, which span-wise plane you're considering if you're using computational data that has multiple planes, or if you're using three-dimensional data, and which phase you're considering of the model. And we're going to average a given field variable. So we can do small scale streamwise velocity field. We can do anything we want for Q. We're always going to use the streamwise velocity for this projection. But we're going to average that. This is just an average, where we include any snapshots that satisfy two conditions. One, that the projection coefficient has to be sufficiently good. That's actually this one. It has to be better than some threshold that tells us that we saw something that looked like the model. And then it has to be the best projection coefficient of all of the phases you considered, which is kind of what I was doing visually here. I said, which of these is the best comparison? It's this one. I'm going to label it with this. So this condition here is saying that the projection coefficient you find for this phase has to be better than any other phase that you considered. So what model do we use? We're going to use a Resolve It model in this particular talk, but you can use any model that has an associated phase with it. So this is just instantaneous images that indicate that just three modes added with a mean from a Resolve It analysis really replicates a lot of the structural features that we would expect from instantaneous visualizations of turbulent boundary layers. And so this gives us some qualitative hope that this is not a terrible structural representation of our flow. Okay, so again, we're going to do this conditional projection averaging. We're going to take our data, we're going to label it with some phase by doing a projection onto a model, and then we're going to average all of the snapshots that have the same approximated phase. All right, what does this give us? So up top, I've done this for a model of a large scale motion, which means I'm placing this in the outer region, the wake of our boundary layer. The convection velocity associated with this model is 0.8 in infinity, which means it's up pretty high up. And we can see that what we get back in the averaged streamwise velocity field looks, I can tell you, looks like our model, which is not a surprise. It has inclined alternating structure pattern. I've paneled our results here. These are all averages at different phases, and I've paneled them together so we can see a full period of the phase of this large scale. So what I've extracted really is kind of the clean and smooth phase variation of a large scale structure based on a comparison to a model. And then I can ask, compared to this phase variation, what do other things do in the flow? So this is really just getting back what I asked for. This isn't a surprise. This is the stuff that's interesting. So these are also varying with this phase. I'm asking in these pictures, how does small scale streamwise velocity intensity change with this phase of this structure? How does wall normal streamwise small scale velocity intensity change with this phase? And this black line is just this information plus the mean. So you can kind of see that kind of total velocity perspective, which is shown here at the ISO contour where it matches the velocity, convection velocity of this model. All right, what do we actually see in these pictures? So let's start with this small scale streamwise velocity field intensity. So we see some things we should expect. So the small scale intensity appears stronger near the wall in the presence of large scale positive structures and stronger farther from the wall if we scan across in the presence of large scale negative structures. That's consistent with what has been observed by many others in this field. But we also see a pretty smooth variation of height without a tremendous amount of change of amplitude. We said some changes of amplitude here, but if I scan across in this kind of outer region, for now, not worrying so much about the logarithmic region. And then with the wake, I don't see a tremendous change of this kind of maximum amplitude out here, but I do see a change in where that maximum is happening. So this to me looks like an organization, a spatial variation in where small scales are sitting, rather necessarily than a change of amplitude. And I could make a similar argument, although it's a little bit more muddy for the wall normal, that there's a kind of change in the height where I'm seeing small scales as a function of the phase of this large scale, although we also see some change in this case, more clear change in the amplitude as well across the phase of the large scale. What I can also do though is I can look at what's happening a little bit closer to the wall as well, just by changing my color bar, and we can see that we do see more amplitude modulation potentially, or more amplitude change in the small scales near the wall. And then for the span-wise velocity, which we can only get from DNS, this is actually from simulation, we actually saw very little amplitude, height variation in the outer region, and we really only saw activity in the logarithmic region, and we saw significant changes in amplitude. So we see much stronger in the presence of large scale positive and much weaker in the presence of large scale negative at the wall for the span-wise, which we didn't see in this outer region really. I'm going to kind of run through all this and then we'll try to synthesize because there's a lot of information here. We can do this again with a different model. So the results are highly dependent on what model you choose, and that sounds like a bad thing, but it's actually very powerful. So if we instead define, a superstructure or very large scale motion that we expect to live in the logarithmic region with a conduction velocity that puts it closer to the wall. This is now all shown in log axis, so we can kind of zoom in near the wall more easily. Here's my large scale, again, over a single period, kind of patterned. This is using DNS data, so we can see closer to the wall. And this is kind of a mix of DNS and an experiment. We can now, again, ask this question of how do the different components of the small scale velocity intensity behave? So the small scale streamline velocity intensity, we see again some potentially changes in kind of the height where it's occurring, but also changes in its amplitude. V seems to be pretty happy just hanging out in the wake. We don't see that much activity in the logarithmic region, and we see pretty significant changes in its amplitude. The span-wise velocity, interestingly, I think we see quite considerable changes in the height where it's most active without significant changes in its amplitude. And the small scale streamline behavior very near the wall, if we change our color bar to really focus at the near wall cycle, we see considerable amplitude change. So I'm throwing a lot of different things at you. I wanted to understand how much do we see height variation? How much do we see amplitude variation? So this is the picture I had started us off with. How much do we see things sitting at one height and changing strength versus how much do we see things kind of staying the same strength but changing height? And my takeaway from the data that I just showed you, and you can look at the 2022 paper cited here, it's in Physical Review Fluids, is that we see both. That they're both there from what I see. And so this, for us, yields this kind of a picture where my distillation of that information is that if you're in the same region of the flow as the large scale, so if you're looking at small scales that are really active in the wake, and you're asking about a large scale motion that lives in the wake, then most of what you see is the fact that the large scale motions are distorting that part of the flow. And by distorting, I mean moving things around. The small scale seems organized around that large scale. But if I look for a small scale that's most active, strongest at a different part of the flow, let's say nearer to the wall than the large scale that I'm averaging on, that I instead largely see amplitude variation, which I'm showing here with this change of color to green. And similarly, if I look at farther from the wall than where the large scale is, if I ask about the superstructures in the wake, but I then look at V that is most active in the, superstructures in the logarithmic region, but I then look at V that's most active in the wake, I again mostly see an amplitude change. So my synthesis here is that there's both kind of spatial distribution of small scales and genuine amplitude change, depending on which large scale you're asking about and whether the small scales you're interested in are really strong at that location. And this isn't so dissimilar from what Ganapathy Subramani et al. Said in this paper, that there's kind of true modulation in some regions and more of an organization in others. There's a lot we can talk about here. We also wanted to ask this question of, is it really the case that there are some really coherent structures that are kind of spatially distributed and everything else is kind of small scale fluctuations that aren't really coherent? And so to try to probe that question, another kind of analysis we did was we used vortex tracking to look for strong vortices in our flow field, and then noted how far they were from the wall as YV. And then we conditionally averaged the large scale velocity on how far from the wall our structure was. So if we found a vortex far from the wall, we would average those together. If we found a vortex near the wall, we'd average those together. And we asked, are they associated with different velocity fields? And the answer, unsurprisingly, was yes. So if we averaged all the flow fields that were associated with coherent vortices that were sufficiently strong, that were near to the wall in the average height, then we got back a large scale positive. And if we averaged all the snapshots that had a coherent structure that was coherent vortex that was far from the wall, we got a large scale negative structure. So this is consistent with what we would expect, but it also kind of goes back to the suggestion that in some cases, at least, that is suggestive that there might be kind of a height variation component with particularly strong coherent structures. And this is also consistent, of course, with other people's visions here. I'm showing a picture by Adrian that has small hairpin vortices on top of large-scale structures like we're seeing here. And then also this nice paper by Marusik et al. From Science 2010, where they show small-scale vorticity below large-scale positive and above large-scale negative as well. But this still doesn't really tell us mechanism. So I think that the conditional projection averaging is helpful. It helps us really get a smooth variation in phase of large scales, which can be nice, and ask also specific questions about which large scale you're interested in. And it can help us try to pull apart kind of amplitude versus height variation, but it doesn't really tell us still how that's happening. And so we were interested, there's been a lot of work on kind of amplitude change, and so I wanted to focus to start on this height change, and I wanted to ask what mechanisms could generate this kind of organization, this kind of height change of small scales around large scales. And the two of the ones I thought of were, or other people have thought of too, are amplification, that you could have small scale kind of growing along a shear layer, for example, and some kind of an instability. Or you could have advection, you could have small scales being moved by the wall normal velocity component, for example, to be kind of up in the presence of a large negative U, positive V, and down in the presence of a large negative V, positive U. And I was interested in whether we could pull apart these two and ask, again, questions about which of these two mechanisms was most dominant. We are looking at both of these mechanisms. I'm not going to talk about our amplification work today, but we're doing some, I think, fun work on that. But I'm going to focus today on the advection work that we're trying to do. So we thought we'd set up a new experiment to try to ask questions about advection between small scales and large scale coherent structures. And so what we did is we kind of artificially added in new small scales at a fixed height. So we put a von Karman vortex tree, we put a small cylinder in our boundary layer at a fixed height, and then we looked at where the vortices go downstream. Do they change height? Do we see advection of these vortices that start at one height under the influence of the large-scale coherent structures of the turbulent boundary layer? And then, we'd have to make arguments about whether or not that's relevant to naturally occurring small-scale vortices. So to do this experiment, we put a cylinder that spanned the full span-wide extent of our wind tunnel. We made sure that the Reynolds number for the cylinder was high enough that we would have vortex shedding, which it certainly was. And then we put the cylinder at several different heights. And actually, here I've listed 5 heights, but really there are 6. There's another one at like 1.1, so a little bit outside the boundary layer. So it's really all in, like the wake region of the boundary layer, starting at 0.375 delta, going up out of the boundary layer height. And we took some non-time resolved and some time resolved images of this flow. There have been a lot of other work. There's lots of work studying the interaction of boundary layers and wakes that are really fascinating. Work looking at, what the impact is of different turbulence intensities on wakes. There's work, lots of work looking at the wakes of wind turbines interacting with boundary layers, of course. But there's also a lot of work actually, even with really similar setups. So what we're considering a cylinder kind of in the span-wise direction, extending across the boundary layer. Usually the cylinders are larger relative to the boundary layer than what we're studying, but it's a similar setup. And we have some papers we can kind of look to. There's some nice papers from the 70s about this interaction that we can refer to make sure that what we're seeing makes sense. And there's also been quite a lot of work specifically thinking about the advection of wakes. So this is a really pretty picture, I think, of a Von-Karman vortex street in a circular flow. That's just really beautifully circular. And then, in the context of wind turbines, there's been a lot of work thinking about advection, mostly in the span-wise direction, the kind of meandering of the wake under the influence of turbulence. And so we can hopefully ultimately make connections to that as well, because we're really interested essentially in meandering of this wake, but understanding it as a direct impact of the coherent structures. So we have statistics for this flow. We did experiments on this in the fall, I think. I'm not going to talk much about the statistics today, but we're working on a paper about that. But we see that nearest downstream of the cylinder, we see a significant impact on the mean velocity profile that kind of decays as a function of space. But over our field of view, we still see a significant change to the mean from that wake, and we can see similar significant impacts on the U squared and V squared statistics that decay as you go farther away from the cylinder location, particularly decay well in V. And we're comparing these to some of the statistics from the 70s and seeing good comparisons to the extent that they're comparable. Their cylinders were a little bit larger than ours. But I want to go back to using the conditional projection averaging technique that I used before, and I'll say that the results I'm going to show here are pretty preliminary. I think there's a lot more we can do here, but I think there's some interesting results I wanted to share and some kind of suggestive results. So again, we're going to do this conditional projection average. We're going to compare instantaneous snapshots to a model. This time we're not going to use a resolvent model because we don't have a canonical flow, and so resolvent analysis is a little bit inconvenient. So we're going to use Spectral POD, which also gives us back modes that have a really clean definition of phase, which is nice. So we did Spectral POD on the modified flow. So you can see here a specific, first mode at a wavelength around 6 delta. And you can see that the mode is significantly affected by this wake that's kind of disrupting it at a particular height. And so you could also argue that you could use the undisturbed flow to get your SPOD modes, and we're exploring that, but I like using the disturbed flow for now. So we get modes. This is the same mode at 4 different phases. We're again going to project onto these modes, and just for fun, I thought I would show you that we also, of course, get cylinder shedding frequency modes as well that we're studying separately. This is the case where the cylinder is nearest to the wall of all the cases that we've studied so far. For this case, because we have such a strong change of the behavior as we go farther downstream of the cylinder, I'm going to separately show you results upstream, midstream, and downstream. We actually do the conditional projection averaging using the whole field. I'm just going to show you the results separately because then I can tune the color bars to let you see what's happening in each region, because it's significant kind of decay as a function of X. So I'll show you, each of these regions on their own. So let's look at some results. So everything I'm going to show you is all happening here. So this x-axis is not showing you streamwise extent, it's really showing you phase. So here's my averaged streamwise fluctuation velocity. So this is what I'm kind of asking for using my model. I'm getting back something very similar to what I asked for, which is the phase variation. Not quite as clean, I don't have as many snapshots. It's something that I think we can resolve this better and something that's on the to-do list. But these ones have fewer snapshots embedded in them. We can also look at V. We see that negative V is associated with positive U. Positive V is associated with negative U. That's not a surprise. And then across this phase variation of large scale that we get from our conditional projection averaging, we can also ask, again, each of these panels is at the same X location, just downstream of the cylinder. How does this phase change what the wake does? So this is a wake at different, depending on what the local phase of the large scale is doing for U squared and for V squared of small scale. That's filtered out the large stuff. And from my eye, the wake seems pretty agnostic to the large scale phase. It looks quite similar, and we can do more quantitative analysis than just eyeballing that, of course, but I don't see a significant change of the wake immediately downstream of the cylinder, depending on what the large scales do. But if we start looking downstream, so let's look at the midstream, this middle region, I start seeing more change. So the large scales start looking a little bit healthier. They're not quite so disturbed by the cylinder anymore. So U and V are starting to look a little bit more normal. But we can look at the small scale behavior and see some interesting features, I think. We see significant difference in that behavior in the shear layer. I see it being stronger, higher than it started in this area, and just generally stronger in this area. We see, I think, weakening potentially in this large scale flow region, and we certainly see weakening in V, which I think is really interesting. So it's been fun to kind of watch how the local behavior of the large scale seems to be statistically changing, how this wake changes and is affected. And I think we see also some increase of intensity nearer to the wall in the presence of this large scale positive compared to where it started. And we can look farther downstream still, and we continue to see change in the height. So we see that in the presence of this large scale flow and positive V features, that the wake intensity seems to be drifting up for both U and V. So these results, I think, are suggestive that we can use this kind of an experiment to ask questions about mechanisms. We do see advection, I think, of the wake by the V component, the wall normal component of these large scale structures. But we're also seeing amplitude change that I'm really interested in and looking forward to studying more. You know, we can see here, I think, a weakening in this kind of negative to positive transition of the large scale phase. So preliminary, but we're really excited about them. And as you might imagine, all of this is very dependent on the model you choose, as we talked about before. So if I choose a different model, or I'll say that choose the same model to start, but I choose a different cylinder height, we have a lot of them, we can see different behaviors. So if we choose a higher cylinder height with the same model, the model kind of now lives nearer to the wall than the cylinder is sitting. We again don't see significant change just downstream of the cylinder. And as we look farther downstream, we do see some change. We do see some variation as a function of phase, but it's less pronounced. It's less clear. And I think this suggests that it matters which structure you're asking about. This structure lives near to the wall. The cylinder doesn't. And so if you instead choose a structure that sits farther from the wall, and here I'm just showing out less of the data, I'm just showing U and U squared just to make our lives a little easier. If I choose a structure that lives farther from the wall and associated with the wake instead of with the logarithmic region, then I think we again start seeing a lot more change again. We start seeing significant changes in height depending whether we're in a large scale slow or large scale fast region. And that continues to persist as we go downstream, as well as some changes potentially in the amplitude. Okay, so I want to give myself some time to interpret and take away some of what we're talking about here. For this particular problem, what we're seeing is that we do think that the wake is affected by the local phase of large-scale turbulent structures. We think it matters which structure you consider and which wake height you consider. We generally don't see much of an effect right behind the cylinder. It doesn't seem to significantly affect that so far, though we're going to look at frequency analyses and see whether there are other changes that we can observe immediately behind the cylinder depending on the large-scale structure behavior. But we do see both amplitude and height variation farther downstream, and it's a function of what the large-scale structure is and where the small scales are sitting. And then there's questions about whether these are going to be similar or different mechanisms from natural turbulent structures, but I think I'm hopeful that we'll be able to learn a lot using kind of vortex tracking on it. That's just one of the next steps we're going to do, is starting to really track individual vortices and understand what happens to them more directly to try to understand what's going on here. I'm going to summarize and then just have one future work slide and we can start chatting. So overall, I'm interested in this, at least in this part of my portfolio, and understanding how large and small scale structures are organized. We use conditional projection averaging to look at that and tried to understand a detailed relationship between small scale intensity and large scale phase. We found organization and modulation or height and amplitude change in the canonical turbulent boundary layer and in the turbulent boundary layer interacting with awake. And some of the things we're going to do as we go forward, we are looking at this amplification mechanism too. This is a figure from someone else's paper, but it's suggesting a critical layer amplification mechanisms that can happen along curved surfaces. We're interested in trying to ask whether there might be a critical layer amplification mechanism that could happen along the large scale structures. And we're also doing what we're calling scale dependent POD, and just to kind of, I didn't have time in this talk to really get into it, but if I use a toy problem where I have some relationship between large and small scales, and I do standard POD, it gets the large scales pretty well. You can see these two good singular values associated with those large scales, but it needs a ton of modes to get the small scales right, because there's a nonlinear interaction, nonlinear relationship between the large and small scales, and it gives you back modes that look like this. They look totally wrong. And we're working on a new technique that gives you back much better modes, and you don't need a bunch of modes to explain it. So that's something we're working on now. And with that, I will stop and I will take any questions, and I really appreciate your attention, and I hope that we can have a fun conversation.
Thanks, Jess. That was an excellent talk and great work. Do we have any questions from the audience? Please feel free to go ahead and unmute your mic. All right, while they gather their thoughts, I had one question. Sorry, is there someone from the audience? Oh, no. For the initial part, did you combine experimental and numerical data?
Great question. We use both. I didn't really do a great job of distinguishing them, but we used experimental data a lot because we had more snapshots of it. We could get more converged results. But we didn't have W in our experimental data. It was only planar PAV, and we also couldn't see terribly close to the wall. So anytime you see W, this is actually from computational data. We were happy to see the results from the computational and experimental data were quite consistent, and so we just reported whichever one made the most sense to report, but they were, we could do it on either case, and we saw very similar outcomes.
Tess, thanks for your talk. I have a question about, did you look at the convection velocity? Do you know if the large and small scales were like in the way you captured them? Do you know if they're traveling around the same speed, or like was one kind of, yeah? Any comments on?
It's a great. Yeah, so I know a lot about the convection velocity of the large scale, but I don't have yet a good amount of information about the convection velocity of the small scale. I think we're interested in trying to use some combination of vortex tracking potentially to do that, which we have kind of set up now. But in the original way that I was doing this, I was just kind of squaring the small scales and averaging them without really thinking about their convection velocity. And I think it's a really good question, right? Because it suggests whether there's going to be kind of a phase change and whether the small scales are going to move along or just stay locked with the large scales. And I don't have an answer for you yet. I suspect they're similar speeds. And I actually wonder if it's kind of a critical layer thing here where the small scales move at that speed and sit at the height where their speed matches the local large scale flow, not the local mean. But I don't have evidence yet really for that.
Thanks.
Yeah.
Here we go. I'm on? I think so, yeah. Can I ask a question?
Yeah, go ahead.
Yes, please.
Yeah. Are you implying that there are vortices of opposite signs? You know, when you draw sort of clockwise and then anti-clockwise vortices, are you implying there are vortices of two different signs in your boundary layer?
Great question.
Let's just go back to slide 21, the next slide.
Yeah, this picture up top.
There's a picture on top. So you see you draw clockwise vortices, and then above the pink structure, you got anti-clockwise vortices. Are there anti-clockwise vortices or vortices of the opposite sign?
It's a great question. So I will say that's not actually my figure. I've stolen that picture from Ganapathy Subramani et al. In 2012, I think. So I don't personally think I see many counter-rotating vortices, like rotating vortices the other way. But I think what they're suggesting there is that essentially when you add that with a mean shear, you're going to get stagnation flows back. So I think that must be a reflection of them thinking about it without mean shear or something. But I'd have to go back to their paper to understand in more detail what they're suggesting with that figure.
To work out some way of defining a vortex. How do you define your vortices?
Yeah. I'm only thinking about them being, all the vortices I'm thinking about are rotating clockwise. Yeah.
Clockwise, not counterclockwise. But you got counterclockwise vortices there.
Yeah, that's not my figure, but I think that I'm sure they did something very thoughtful. They're very good researchers, but I don't remember exactly what they're referring to in that figure.
Okay.
But good question, and I should know because it's on my slide. So thank you for asking, and I will make sure that I can answer that question for the next seminar.
Tess, on a related note, can you relate this to the ejection and sweep events that we have?
Yeah, great question. Yeah, I think that these are actually very consistent, and I should have cited it in the 2022 paper, but I should cite it in the presentation as well. I think it's very consistent with ejection and sweep ideas. So in the same way that we can kind of picture in this kind of an imagination, the large scales kind of moving the small scales around maybe, that's similar to the idea of an ejection or a sweep, right? Kind of washing things out or kind of.
Oh, yeah.
So I think it's highly consistent actually with that vision of it. And my aim here is to kind of connect all these different pictures that I think are all right? So we have ejections and sweeps, which are very thoughtful. We have hairpin packets, we have amplitude modulation, and I think they're all kind of saying the same thing. And so trying to find ways of tying all that together and saying that there's some spatial organization, there's some amplitude variation. We're all quantifying the same thing. So but it definitely connects to ejections and sweeps.
All right.
And I put in the chat as well. Great question.
Oh,
I didn't talk about that very much. So the black lines here, really good question. This relates to a hypothesis that I have not yet proven. So the black lines here are the sum of, so it's defined here, it's the sum of this result with the average. And so I'm drawing, instead of drawing like just a fluctuation, right, and faster than the mean or slower than the mean, I'm drawing an isocontour of the velocity, of the average velocity, including the mean. And so if you add the mean back onto these fluctuations, what you actually see is a wave, really, in height. And I can see it also in the instantaneous picture. I think it's a pretty way of looking at it. So this picture here, it's the same thing as this green surface. It's the addition of this large scale field with the mean. And so it takes a fluctuation and it makes it really that isocontour rises with negative and falls with positive. And it's just an algebraic relationship. And what I'm drawing out by putting those black lines in is partially that it kind of helps you see the physical relationship between these two different things. You can kind of eyeball it, but also that I think that the small scales might be following that line. And I have a hypothesis with the kind of critical layer amplification mechanism that I haven't talked about so much here, that small scales might be sitting at the height where their speed matches some kind of a large scale flow rather than a mean. So we often think about structures in turbulence sitting at the height where their convection speed matches the mean. But if instead small scales don't know what the mean is, but they can feel the large scale flow around them, then I was interested in whether they were sitting at the height where their speed matched the some local kind of constant speed. So that's what I was trying to draw out here. But since I don't know the small scale speed, as Daniel highlighted, I haven't yet really proven that hypothesis, but it's there to kind of try to draw out that relationship. So yeah, I'm wondering whether these things are just kind of being carried around, at least in part.
Well, I had one last from my side. I was very curious about the first slide that you showed, where you have a moving roof. I was just wondering if you could tell us a bit more about how you, what kind of mechanism do you have in place for moving the roof in there?
Yeah, let's see if we can get it to play again. Yeah. So we can move them pretty fast. We move them at almost 2 meters a second. And they're pneumatic actuators. They're controlled so that we can repeatedly adjust both their extended deformation and the speed of deformation, so we can understand the effective rate of change in addition to the effect of the actual pressure gradient. And we're doing PIV underneath them in that green box that's shown there in the adverse pressure gradient part. We found some really fun results from doing this, that we are seeing significant unsteady effects from doing an unsteady deformation rather than a steady deformation. And the speeds we're doing it, it's not quasi-static. And we're building other geometries too, so we don't only have to do the favorable to adverse pressure gradient, but the favorable to adverse pressure gradient this creates is actually also really interesting, because you have a significant history effect where the flow in the adverse pressure gradient has been really, really weakened by the favorable pressure, or maybe not weakened, the turbulence has been weakened by the favorable pressure gradient. And so we're also seeing some really fun kind of spatial and temporal effects that we're drawing out. But yeah, it's a nice mechanism. We just for this paper, the paper on experiments in fluids that just came out that talks about this experiment that we built. But it's been very robust actually, and given us some very repeatable pressure signals.
Great, fantastic. Thanks.
Yeah, we're going to try to share a lot of data so that computationalists can compare to it, since it's, you know, it's rare to get a lot of unsteady turbulence, like globally unsteady turbulence data.
Yeah. Right. Any other questions from the audience? Well, if no, then please join me in thanking Tess. That was an excellent talk, and I think we had a very fruitful interaction in the Q&A session.
Yeah, thank you all so much for coming, and I'm really glad we got to chat a little bit, and I hope that we can all see each other in person someday.
Oh, sure. All right. Thank you very much, and I'll see you all next week. Stop recording.
Thank you.